start recording. So convex functions and concave functions, so they are right. So they are functions that have the characteristic that the chord lies either completely below or completely above, or the curve lies completely below the chord or above the chord. In the convex case, if I draw a chord, okay, the part of the function between the 2 points where the chord meets the curve. Okay, so this part of the function is completely below the chord. Okay, in a concave function, it is completely above. Okay, so one way to write this formally is to say that in a convex function, if I look at the value of the function at any point, okay, so suppose this is x1 and this is x2, okay, any point in between x1 and x2 is lambda times x1 plus 1 minus lambda times x2. Okay, where so here, like, I divide the interval between x1 and x2 in the ratio 1 minus lambda and lambda. Okay, so any point between them is lambda times x1 plus 1 minus lambda times x2, and here z lambda will be a number between 0 and 1. Okay, so these are the points between x1 and x2. The value of the function at any point, so let's say that this point between x1 and x2 that we have chosen is x star. Okay, convex function is one where the value of the function, okay, so in a convex function, the value of the function at any point between x1 and x2, okay, is less than the interpolated value of the function. So the value of the function is less than the linear interpolation of the values. Okay, so this is a convex function. In a concave function, okay, the value of the function is greater than the interpolated values. Right, so if a function f is convex, okay, minus f is concave, and if a function g is concave, okay, minus g will be convex. Okay, so because when you change the sign of the function, this inequality gets reversed. Okay, if I multiply both sides of inequality by a negative sign, okay, I change the direction of inequality, right? So for that reason, like, if you have a convex function, negative of that function is concave and vice versa. Okay, so these are like general definitions of convex and concave, but where the functions are continuously are differentiable everywhere, okay, or if the second derivative of the function exists everywhere, there's a very simple way to characterize it. So in a convex function, Okay, so what should the second derivative satisfy for a function to be convex? Okay, so if you have a function that is like this, okay, this is convex. Okay, so that means the derivatives are at different points, they're like this. Okay, the slope, the tangents, the slope of these tangents, these are the derivatives. Okay, what is happening to the derivative?
It'll be a constant value.
Yeah.
So what is happening to the derivative?
It goes from negative to 0 to positive.
Sorry, are you asking about the sign for the second derivative?
Oh, sorry. Right. So, Nick, you're saying something, but I'm unable to hear.
Oh, sorry, I was just asking if you were like getting at the sign of the second derivative.
So, in this example, you can even say something about the sign, but yeah. So, tell me about the sign.
So for convex, it's positive and concave negative.
Right. So, so I was asking about the first derivative. The first derivative is always increasing. So, if you have a convex function, okay, you must have that the first derivative is always increasing. Okay, and therefore the second derivative is always positive. Okay, and it's also easy to see this uh, from by just writing the expression from Taylor's series. Okay, so and when you the same thing, if you're looking at concave functions, okay, the second derivative is always negative. Okay, so it's always non-positive. Okay, so you can, if you want to see it analytically, you want to say that f of x, so if you have a point, x1, okay, let's say you have a point x1, now f of x2. So if I draw a tangent at x1, okay, because the function is convex, the entire function lies above the tangent. Okay, and this means that for any point x2, okay, I've just written x to the right of x1, but it works regardless of which direction. Okay, f of x2 must be greater than the value at this point. Okay, now this point in red is simply f of x1 plus I just go along the tangent, right? So x2 minus x1 times the first derivative of x1. Okay, so but if I expand x2, okay, if I expand f of x2 by Taylor's series, what do I get? F of x2 is by Taylor's series. Okay, let me just write it properly. Because f is convex, f of x2 must be greater than the red point, which is f of x1 plus x2 minus x1 times the first derivative of x1. Okay, but by Taylor's series, So f of x2, expand out Taylor series for me. What's the next term? If I write Taylor series around x1,
The first derivative.
x2 minus x1 times the first derivative, and then we want to truncate the Taylor series at this point. Okay, so the way to do that is this, we'll say this is x2 minus x1 squared, the second derivative of f of x star divided by 2 factorial, where x star lies between x1 and x2. Okay, so the Taylor series for to expand f tells us that f of x2 will be equal to the value at x1 plus the term that corresponds to the first derivative, okay, plus a term that corresponds to the second derivative, okay, but the second derivative is evaluated at some point between x1 and x2. Okay, so this is like combining Taylor series with the mean value theorem. Okay, but when you have something like this, we know that because f is convex, f of x2 must be greater than the first two terms. Okay, that means that the third term that includes the second derivative has to be positive. Okay, so does that make sense? Right, so the derivative thing helps us get some intuition about what is happening. The slope always keeps increasing in a convex function. Okay, but when we have like simple functions which have like the second derivative everywhere, very easy to check if it is convex or concave. The second derivative has to be non-negative for it to be convex, and it has to be non-positive for it to be concave. Okay, so basically like if you have e to the x, the first derivative okay, the first derivative is e to the x, second derivative is also e to the x. Okay, e to the x is always non-negative. Okay, and therefore e to the x is convex. Okay, if you have log of x, what's the first derivative? Let's say this is log to base e. We won't worry about, so for now let's say log to base e so that it's easy. If you have the natural log of x, what is the first derivative? Right, so 1 over x, okay, and the second derivative is negative 1 over x squared, okay, which is always non-positive. Okay, therefore the natural log is concave. Now log to base 2, okay, log to base 2, it's just a scaling of the natural log. Okay, so this is log to base, right? So it's just a scaling. Okay, so the second derivative of right, so since the function is just scaled, okay, the function is simply scaled by a constant that is non-negative. Okay, so all that changes is like the first derivative and second derivative both get multiplied by a positive constant. Okay, so the signs do not really change. Okay, so log to base 2 is also concave, or log to any base. Log to any base which is greater than 1, okay, is also concave. Right, So are we okay on this? Okay, so it turns out these are a couple of functions we'll use a lot, and that's why like we paid a little bit of attention to them. Okay, now, so with the right, so and just to recall, Jensen's inequality is like just building on the definition of convexity or concavity. Okay, so it says that if x is any random variable, and f is convex, then okay, so we are just rewriting. So if x is a binary valued random variable, then this is just the definition of convexity. Okay, but interesting thing is this applies regardless of what the random variable is. Okay, it doesn't have to be binary valued. It can take values. X can take values from a countable set or even all real numbers. Okay, it can even be uncountable. Okay, so but regardless, this the function of the expectation of x will be less than the expectation of function of x. Okay, and of course, like for concave, like this, if g is a concave function, you'll have this inequality in just the reverse direction. Okay, everyone okay with this? Okay, so what we are going to do now is we will use Jensen's inequality in a very particular for the log function. Okay, we are pretty much going to use Jensen's inequality for the log function, and it will be something that is very useful for us. Okay, and we call this the log sum inequality, just a fancy name for something very common. It says that when you have something like this, okay, AI are positive numbers, BI are positive numbers, right? And I'm looking at summation of AI log of the ratio of AI over BI. Of course, the reason we do like this is because this is very similar to the KL divergence. Okay, the only distinction between KL divergence is that AI and BI need not be probability distributions for this result. Okay, each term is each of AI is positive, each of BI is positive. Okay, but it is not necessary that AI add up to 1 or BI add up to 1. Okay, they can add up to some other numbers. They don't have to add up to the same number either. Okay, now the log sum inequality just says that this is greater than or equal to the summation of AI or log summation of BHA. Okay, note that all these i's, let me just use j, k, and l. Okay, this j, k, and l are just dummy variables. Okay, and they're all different. Okay, so as far as the right side is concerned, the terms in the parentheses are just numbers. Okay, the right side just contains one term, which I get by plugging in the summation of AJ, summation of ak and summation of bi. Okay. Unlike the term on the left where this I is the same for all three terms. Okay. Right. So this means that if, for example, let's say a1 equals 1, a2 equals 3, a3 equals 4, b1 equals 2, b2 equals 2, b3 equals, give me some number, something. Okay. Then it tells me that 1 log 1 over 2 plus 3 log 3 over 2 plus 4 log. Right? So this is greater than, so summation of ai is 1 plus 3 plus 4, which is 8. Okay, and summation of bi is 6. Okay, so this is 8 log 8 divided by 6. Okay, does that make sense? Okay, so the equality holds if and only if ai equals 2 times bi for all. Okay, so the equality holds only if ai and bi are proportional. Okay, so for example, if I have ai equals 1, a2 equals 3, a3 equals 4, same as before, but now b1 equals 1 half, b2 equals 3 over 2, and b3 equals 2. Okay, so now ai and bi are proportional, right? So this will be the case where you get equality. And what happens here, every term of the summation on the left is going to be the same. Okay, and in this case this will be equal to 8 log. Every term will be equal, each of these terms is going to be log 2. Okay, each of the log terms on the left will be log 2. Okay, okay, so does that make sense? Right, so right, and one reason we do the log sum inequality is it also clarifies Jensen's inequality for us. Okay. Okay, so this is very easy to prove so long as you notice something. Log, what sort of a function is log?
Concave.
Right, so log is a concave function. Right, so if log is a concave function, then for any random variable, what do we know? How do you relate? Okay, so here we relate two quantities, right? The two quantities that we relate are log of expectation of x, okay, and expectation of log of x. Which direction will be the inequality?
The log of the expectations greater.
Log of expectation is greater. Very good. Okay, so this will be the inequality. So the only thing now is to make up a random variable, okay, so that this works. Okay, so we make up a random variable and a probability distribution so that we have the form that we want. Okay, and the form that we want is Okay. Right. So anyone wants to take a shot at this?
Sorry, the log of EX should be less than expectation of log of X.
Okay. So
Or I make a mistake, sorry.
no. So no, it's this is something that happens all the time. So every time we think about doing this, we have to review this. So anyone who uses this every single time, like you have to imagine what is happening. Okay. What is log? So suppose you have a random variable, it can take on multiple values here. Okay. Tell me what is log of expectation of X. Okay, so let's say that the random variable can take on these two values. Okay, and the expectation is some point here. Okay, so tell me what is going to be what is going to be log of the expectation of X?
It's on the curve.
Right, it's on the curve, so it is this point. Okay, what is the expectation of log of X? So log of X for one of the values is here. Log of X for another of the values is here. Okay, so this is log of one of the values of X can take, log of another of the values X can take. So log X is the random variable that has these two heights. Okay, so the expectation of log of X will be a point here. Okay, so log of expectation of X is indeed greater than or equal to expectation log of X.
Yes, my mistake.
No. Keep in mind, actually, we do this every single time. Okay, we always, so it is actually very common for people to keep doing this. Okay, so let's think of this random variable X. Okay, so where X takes on values AI over BI. Okay, but with probability. Okay, now we are making up a new random variable. Okay, the values the random variable can take equals AI over BI. Okay, for all possible i's. Okay, and the probability with which it takes on this value AI over BI is BI divided by summation of BJ. Okay, what is the expectation of X?
It would just be the summation of BI over summation of BJ
No.
times A over BI.
The expectation of X will be, let's do a little carefully, summation BI over summation of BJ times AI over BI. Right? So this will be the summation of AI divided by the summation of bj. Okay. Now, what is our expectation of log of x?
Is that the log of summation AI with divided by summation PJ?
Okay, so this is summation of log of AI. No, so the value x can take on values AI over bi. Okay, so log of x can be log of AI over bi. Okay, and what we have here is bi over summation of bj for the probabilities. Okay, right? So this is less than or equal to, right? So this tells us that summation of is less than or equal to. So this is what, if we take a random variable like this, okay, this is what the Jensen's inequality immediately gives us. Okay, so the expectation of log of x okay is less than or equal to,
The log of the sum of AI over sum of BJ's.
the log of summation over summation bj. Okay, but this is not quite what we want. Okay, so how do we do this? Right, so this is one way to use Jensen's inequality. It gives us something, but not quite what we want. It tells us that summation log bi over okay, this is not quite what we want. Okay, but it's almost there. Right? So how do we change what we do to get what we want? We are just doing a little bit of seeming trial and error, because this is kind of how you would use in practice. Okay.
Well, we just need to change the the change log to negative log, and it swap the numerator and denominator, and everything become in the form that we want. Just change the location of AI and BI.
Yeah, we don't even need to do negative log. We just notice that this is almost there, because this just tells us that summation bj log a b over a l is less than or equal to summation bi log. Okay, so I multiply both sides by a negative sign. Okay, if I multiply both sides by a negative sign, or I move this one to the left side and this one to the right side, okay, but I have to do it with the negative sign. Okay, and so that's why I changed the order of the ratios. I change inside the log. Okay, This is almost thick, right? The only thing is like the role of A and B are interchanged. Okay, so if you wanted to write it in exactly the correct way, we make a new random variable y, which is bi, which takes on values bi over ai, okay, and probability ai over summation of ai. Okay, when you use Jensen's inequality on this, you'll get exactly the form that you want. So expectation of y is summation of
Excuse me.
no?
Sorry.
Again, this is exactly what we want. So now it's this scaling over. Okay, and if I shift AK, I have log sum inequality. Okay, so but just play around with this. Okay, you can use different combinations of random variables in this. You'll get slightly different rewritings of the log sum inequality. Okay, so right, so there are many other ways to do it. You can also use the fact that the function x log x, okay, you can take the function x log x. What sort of a function is this, concave or convex? Is x log x what sort of a function? So what's the derivative? You can think of this as log to base e. So what's the derivative of x log x?
Is it log x plus 1 over x?
Okay, so this is log x plus, say again, log of x plus?
1 over x?
No,
X, oh, just 1.
yeah, log of x plus 1.
Yeah.
Okay, So the derivative of x log x is the first one, like I just take the derivative with respect to x, and the other one is 1. The second derivative is
Just 1/x.
1 over x. Okay, and if x is positive, okay, and which is why you need ai and bi to be positive. If x is positive, okay, so if x is positive, 1 over x is also, if x is here, like, let's see, if x is positive, 1 over x is also positive. Okay, so x log x is convex, okay, for positive values of x. Okay, so if I just restrict my attention to, if I restrict x to be greater than or equal to 0, okay, x log x happens to be a convex function. Just a second, what is happening here? Sorry, I got cut off for just a second. So I got cut off for just a second, like, okay, but is this okay? So when we look at just positive values of x, okay, x log x happens to be convex. Okay, try to use this with Jensen's inequality to show the log sum inequality. Okay, we'll leave this for homework because I think your textbook actually uses this approach. Okay, so but you can do it anyway, like you can do it many different ways. Okay, so does that make sense? Okay, right. So one of the immediate consequences of log sum inequality is, since the only restriction for the log sum inequality is that the ai and bi happen to be positive. Okay, so if ai and bi, if we take any two probability distributions, okay, then let us say p and q. Okay, so p and q are probability distributions, so they assign, so what their support is not so crucial right now. Okay, just the values of the probabilities are what we are concerned about. Okay, so maybe like the universe has size 10 and p assigns to each of these 10 elements some probability, but it's like a sequence of numbers, one for every element of the universe, and q is the same. Okay, q is a probability distribution on the same universe. Okay, so but we don't care what the universe is. All we are concerned about here is, like, these are two probability distributions on the same universe. So if you look at it as a sequence of numbers, there are two sequences of positive numbers, or two sequences of non-negative numbers. Okay, and the length of these sequences is the same. Okay, and so you can use log sum inequality. Okay, so let's say that the values of the probability are p1 through pk, right? So this means that k elements in the universe and the probabilities assigned to them are p1 through pk by probability distribution p, and distribution q assigns then q1 through pk. Okay, So the log sum inequality now means that summation pi log pi over qi, okay, is greater than or equal to summation of log pj log of summation of pk. Okay, but these are probability distributions. So what is the summation of all the pi's?
Just one.
1, right? So log of 1 divided by 1, which is 0. Okay, but the quantity on the left, what is this? So we defined this quantity on the left last class,
The divergence.
right? So it's the Kale divergence between P and Q. Okay, so the Kale divergence between P and Q is defined in this form, and that will always be non-negative. Okay, and it is equal when the two probability distributions are proportional. Okay, but both the probabilities add up to 1. Both the probability distributions add up to 1 on the universe. Okay, so if the only way they can be proportional is if they are equal. Okay, okay, does that make sense? Okay. Okay, so this immediately means one more thing. Okay, the Kale distance, if we looked at the mutual information between two random variables x and y, okay, this is the amount of information one of the observation of one random variable tells you about the other. Okay, now what do we know about this? We know that this is equal to h of x minus h of x given y. This is also h of y minus h of y given x. Okay, but another way we could write it was also that it's the distance between the joint distribution of xy, okay, and a hypothetical distribution which happens to be like the product of their marginals. Okay, so the joint distribution of x and y is the reality. Okay, that's the real joint distribution between x and y. Okay, you can think of an alternate universe where these x and y happen to be independent but with the same marginals. Okay, if they were independent with the same marginals, the distribution in that alternate universe would have been probability of x times probability y for product of the marginals. Okay, so the difference between the real distribution, that is the joint probability between xy, and the product of the marginals is the mutual information. Okay, it's how far away the joint distribution is from independence. Okay, so but this mutual information is a Kale divergence. What these distributions are is irrelevant. Okay, but it's the Kale divergence between two distributions, and we know that the Kale divergence is always non-negative. Okay, from what we just saw, since the Kale divergence is non-negative, we know that the mutual information also has to be non-negative. Okay, so this means that if you observe one random variable, okay, the amount of information it tells you about the other is always greater than or equal to 0. And it is equal to 0 when the Kale divergence is equal to 0. That means that the joint distribution is the product of the marginals. Okay, that means that x and y are independent. Okay. right? So whenever you have two random variables that are not independent, okay, they always tell you information about each other. Okay, one other corollary from the same thing. Since the mutual information is equal to h of x minus h of x given y, okay, this mutual information is always positive. Another way of seeing this is to say that h of x given y is always less than or equal to h of x. Okay, so observation with with equality, if and only if x and y are independent. Okay, so if I observe y first, okay, and then make an observation on x, the incremental information I get when the information I acquire when I observe x in the second step, okay, it's always less than the information I would have acquired when I just observed x. Okay, so that means that in the first step, y has given me some information potentially. Okay, the only case where that does not happen is if x and y are independent. Okay, and then y gives no information about x. So in the second step, the amount of information you acquire is as if you never saw y. Okay, so does that make sense? This requires a little bit of clarification. Okay, the conditional entropy of x given y is always less than or equal to the entropy of x. Okay, now on the left side, the conditional entropy of x given y, it is so the conditional entropy of x given y, right? So this is, I take every possible value for the random variable y, okay, and I look at the entropy of x given that particular, given the event that I observed the value little y for the random variable y. Okay, so this was the conditional entropy of x given y. Okay, and now, so this is the average over all possible observations of y. Okay, and this is always less than or equal to h of x, right? But it is quite possible that h of x that h of x given y equals little y for a particular value of little y, okay, is greater than h of x. Okay, if I take one specific value for little y, okay, it's quite possible that the entropy of x given y equals little y is actually greater than h of x. Okay, so we'll do like a little example. Like let's look at a joint distribution of x and y that looks like this. When I want a condition on y, right? So we consider and y equals 1 is this is do 1/4. Let's look at this. Okay, so what is h of x? Okay, so it's a little bit of practice again. So what is the probability x equals 1?
Did you say the probability that x equals 1?
Yeah,
So 1/4.
1/4. So what's h of x?
Uh,
Right, so it's 1/4 because sum of these two values. Okay, and that is 1/4. Okay, so h of x is 1/4 log 4 plus 3/4 log 4 divided by 3. Okay, and this one is 1/4 log 4. So this is log 4 plus minus. Right, so 1/4. Okay, right. So okay, so let's see like okay, so what is h of x given y equals 0? So if y equals 0, what's the probability of x equals 0 given y equals 0? Right, so the event y equals 0 is these two rows. Okay, so I
It's
take
1/2.
right, so I take these two probabilities, normalize to make it a probability distribution. Okay, so they are equal probabilities, so when I normalize, this will be 1/2. Very good. So this is this is also equal to the probability of x equals 1 given y equals 0. Okay, now so this entropy will be h of x given y equals 0 will be 1/2 log 2 plus 1/2 log 2, which is 1. Okay, and what is h of x given y equals 1? What's the probability x equals 0 given y equals 1?
um 1.
The probability x equals 0 given y equals 1 is 1. Again, h of x given y equals 1 is 1 log 1 plus 0 log 0. Okay, by convention, we take 0 log 0 to be the limit of x log x as x goes to 0. Okay. We define it to be 0. And this happens to be the limit as x goes to 0 of x log x. Okay. So 1 log 1 is 0 and 0 log 0 is 0. Okay, and so this is 0. So this means that when y is equal to 1, if you observe y equals 1, okay, observing x gives you no information. Okay, because if y equals 1, you know x has to be equal to 0. Okay, observing the random variable has not, I mean, you don't get anything by observing the random variable again. Okay, even without observations, you already know that when y equals 1, x has to be equal to 0. Okay, you don't actually have to see it, right? Right, so in this case, okay, h of x given y equals 0 is 1, h of x given y equals 1 is 0. Okay, the conditional entropy of h of x given y, okay, this is the probability y equals 0. So what is the probability that y equals 0? 1/2. Okay, the probability y equals 0 is the sum of these two rows. Okay, the probability y equals 0 is 1/4 plus 1/4, which is 1/2. Okay, plus 1/2 times h of x given y equals 1. Okay, and this will be 1/2 times 1 plus 1/2 times 0, which is 1/2. Okay, so h of x given y will be less than or equal to h of x. Okay, but in this case, h of x given y equals 0 is actually greater than h of x. Okay, which is greater than h of x, which is 2 minus log 3/4. Okay, and the reason I know this is from a different, I mean, you can compute this. Can anyone quickly compute the right side? Remember, this is to log 2 base 2.
I got 0.81.
Okay, 0.81. Okay, so Dylan computes this. Yeah, so it looks about right, but there's a different way I know that this is definitely less than 1. Okay, so in this case, okay, h of x given y equals 0 is 1, which is greater than h of x. That is completely okay. Okay, we are not ruling that out. Okay, so a particular piece of evidence may actually tell you, a particular piece of evidence can actually help or hurt, like the amount of information you acquire. Okay, but on an average, h of x, on an average, observing y always reduces the uncertainty in x. Okay, so in this case, see it this way, when y equals 0, okay, we actually increase the uncertainty in x. Okay, so if we observe that y equals 0, in the next step, observing x gives us 1 bit of information. Okay, but if we observe that y equals 1, in the next step, we get no information at all by observing x. Okay, so but this is conditioned on like a particular observation of y. Okay, but that is not what is captured by h of x given y. h of x given y is on an average. Okay, it's not a specific observation of y that matters here. It's like on an average over all possible observations of y. Okay, what is the amount of information that you get when you observe x in the second step? Okay, so this means that h of x given y on an average, okay, is less than h of x always, less than or equal to h of x always. Okay, but for an individual observation, okay, you could increase the uncertainty in x once you observe that y equals 0 here. Okay, so if for example you saw that y equals 0, okay, you know that in the next step you actually acquire one bit of information when you see x. Okay, does this make sense? Okay, right. So one of the ways I know for sure that this inequality would hold is because I know something else about, convexity tells me something else. Okay, so if I have a random variable x and x takes on values in the set 1, 2, 3 to n. Okay, suppose I have a random variable x which takes on values in a set of size n. Okay, I know that the entropy of x is less than or equal to log n. Okay, so what is log m? Log m is how many bits you would have needed to describe all, if you wrote like binary descriptions of each of these elements, okay, you would have needed log m bits. Okay, and sure enough, if x is a random variable that takes on values from the set 1 through m, okay, the entropy of x, the amount of information that you acquire when you observe x is less than or equal to log m. Okay, and to prove this is quite simple. Like what you do is, like, let us say that p is a uniform distribution, or let's say q is a uniform distribution on 1 through p is a uniform distribution on 1 through n. Okay, let us say that x is distributed according to p. Okay, that means that probability of 1 is the probability that the random variable x takes the value 1. Okay. So let us say that p is a distribution, so it gives each of 1 through m some probability, and we'll call this p1 through pn. So this means that the probability x equals I is p1. Okay, for all numbers 1 through n. Okay, now what is the KL divergence between p and q? Right, so this is summation pi log pi over qi. Okay, but qi is just uniform, right? So qi is 1 over m for all m, right? So this is pi log pi divided by 1 over n. Okay, now I'm going to just write this as summation pi log n plus pi log pi. Okay, now summation of, in the first summation, okay, summation of the probabilities is 1, so the first summation is just log n. Okay, the second summation is just negative entropy of x. Okay, because entropy of x is summation of pi log 1 over pi. Okay, with a negative sign, it's just negative entropy of x. Okay, but I know that the KL divergence is always positive, or it's always non-negative, right? Since the KL divergence is always non-negative, we must have log m minus h of x to be always greater than or equal to 0. Okay. Or that the entropy of x has to be less than log n. Okay, that's how I knew this without computing. X is binary. Okay, so the entropy of x has to be less than or equal to log of 2, which is 1. Right? So the moment I got this conditional entropy to be equal to 1, I know it is greater than or equal to h of x, because h of x is, because x is binary, h of x has to be less than log 2, which is 1. Okay. So any questions? Okay, so this is probably a good place to stop today. So basically, we have used convexity in basically all our convexity results. That is, h of x given y is less than or equal to h of x, the mutual information is greater than or equal to 0, or h of x is less than or equal to log n. All of this are based upon one application of convexity to show that KL divergence is greater than or equal to 0. Okay, so we have pretty much used convexity on KL divergence, and from that we got all the other things. Okay, so this is one strong way to use convexity. Okay, so I'll leave you to review this. I'm a little behind in uploading classes and everything, but you'll have all of them today. Okay, so let me know if you have any other questions, and we can you can continue asking me questions. I'll stop recording.